yellow folly. I hope you are well rested. Even puppies need a nap after learning KMP. Logarithmic abilities are flowering. Heralding a new week. Welcome back.
Good afternoon. Lovely to see so many of you. Particularly good to know that at least about a third of the class was not too traumatized by either the mid-semester test or KMP. So ready for the second half of semester. So now we start getting into more interesting data structures. We've covered a lot of content already, so we'll now be doing one or two more advanced tricks in C. And then from then, we have a few advanced data structures. And once we're through that, it's almost the end of the class. In fact, we intend to save most of the time for the rest of the class for solidifying what you've learned already rather than adding large amounts of new content. So we do have a few weeks of new data structures, but then we anticipate the last couple of weeks will be extension material, material to enjoy, and material to just help you reflect on what you've learned already. So our class started off with a super high pace. We maintained that for a while. We've got now some material which I would say starts to be a little bit gentler, although can still produce some bugs. And then the end of semester, we kind of reduce the difficulty a bit to give you time to let it all sink in and to do your project work. So with that said, we have the historical figure for this week. This is Barbara Liskov, born in 1939 and the 2008 Turing Award winner. She's a professor at MIT, and she was all about describing the fundamental nature of abstraction, in particular data abstraction. So it's thanks to her that we have concepts such as object-oriented programming and abstract data types. They were really something that she was very foundational in developing. You can also see that on this slide I've put a whole lot of different languages. All of these are languages that, again, without her never would have come to pass. So another key figure in computing. One interesting historical note from the life of Barbara Liskov is that she initially wanted to do her PhD at Princeton. But it being Princeton and it being the mid-20th century, they didn't allow women in. So instead, she went to Stanford, and now Princeton, I'm sure, regrets not having let her in. Fortunately, the world has moved on somewhat since then, and I would encourage you, if any of you are interested in research, no matter what your gender might be, I would really love to come and talk to you about it sometime, and we can talk about the pathways for you to get involved, and maybe one day you too will be on some random professor's slide talking about the amazing contributions that you have made to the field. So with that, I've got, all of you know by this point that I'm a big fan of learning different things about people in the class. And so we're going to continue on in that theme for the very start of today's lecture. If I can turn this thing on. Test 1, 2, test, test, test. There we go. Okay, this is working. Hello, Jerry. Okay, so I've got a new friendly face. These are very, very easy questions. Very easy. You've got the easiest job out of anyone in the class so far.
My name's Nabia, and I'm 20, and I'm from Pakistan.
Okay, what else can you tell us about yourself? Give us like 5 pieces, short facts, like really short facts.
I really love doing maths. I even do it when I'm bored.
So let's call it favorite subject, maths.
Yeah, and
Okay, maybe just give me 2 more.
I'm just thinking.
Do you have any pets?
No, I don't like pets. That's one more
Okay,
thing.
dislikes, animals.
Yeah.
Okay, should we add something to the likes category? One more thing?
Yeah, I love public speaking.
Love public speaking, okay. So this is good for you then. I'll leave the microphone with you for another minute. So it was Nabia, right? Yeah, Nabia here has given us a whole bunch of facts about herself, and now we want to put them in our program. So I'm going to open up a program on this computer here. I'll display it. There we go. I'll call this, once it brings up the dialog, nabia.c. That's how I spell your name, N-A-B-I-A?
Yeah.
Okay, great. So how do I put you in here? This is a C file.
I'm sorry, I can't see. I have to see from my phone.
It's okay, there's nothing in here yet.
Yeah, okay.
So how do I put you in the program?
I just put include nabia.c.
Well, that's probably not going to be super helpful because I don't have a nabia.c. There's nothing there to include. But, you know, I'll give you a hand, and we'll include standard I/O. We'll make a main function. Oh, std. You're right, you're right. Did I hear that from Jerry or Gabriel? OK. Main. Oh. OK, so now I've got a program, but still no nabia. Well, what should I put in? OK, let's go back to our slide for a second. OK.
You want to put all of this?
Well, I want to put all of you in my program.
Oh, okay.
So how should I start doing this?
So we can just make variables like char name and int age and char country, maybe?
It was 20, you said?
Yep.
OK, so let's leave it at that for the minute. Now that looks pretty good. We've now got all of Nabia in our program. But I see a few more of you in the class. Do you want to pass the microphone over, not to Angela, because Angela was spoken to recently, and she's got other things to be doing today. Pass it one more over. What was your name?
Maria.
Maria. OK, so now I want Maria in the program. Tell us a bit about you.
My name is Maria. I'm 19.
Where are you from?
Greece.
Likes, dislikes?
I like maths.
Whoa, 2 people who like maths in a random university classroom? Almost unbelievable. And 1 dislike. You can say me.
Not yet. I don't like cats.
Not yet. Whoa. Don't worry, the exam's coming. We'll change
For
that.
the exam and I'll update. No, I don't like cats.
OK, don't like cats. You two are pretty similar. You should be friends. Don't like animals, like maths. What more is there to life? OK, so how should I put you in the program?
Character, name, Maria.
Is this a good idea?
Yeah, I think. Is it?
What do you guys think?
Oh, it's not.
What have I got up here?
Yeah.
I'm reusing the variable name, so this isn't a very good idea. Well, what else could I do? All of you. OK, name 1, name 2. And I could do, I guess, in age 2 equals 19. OK, let's pass the microphone over. See, lots of people have spoken to a lot. So let's try and pass it back. Pass it back to Aditya. It wasn't Aditya, it was Aditi, sorry. OK, so now you have to, I got your name wrong, so you're going to have to correct me.
Yeah, my name is Aditi. I'm 19 years old.
OK, so let's try that. OK, this isn't good, is it? What should I be doing?
You could probably, if this were Python, I would say create an array of strings, but you know.
Well, it's C, so what are we going to do?
I'm not sure.
You had the right answer 2 seconds ago.
Oh, the array?
Yeah, well, we could use arrays. Remember, we just learned about those, so that seems like a really good way to potentially improve our program. So let's do that. I'm going to create an array, and I'll call this ages. And let's say there are 5 of you in the class. That seems accurate. OK. And I could even set it with some values ahead of time, so 20, 19, and 19. I could do the same for names. OK, but now I need the dislikes thing as well. So let's delete all the ages, because I've got my ages sorted. I'm not going to do an array of strings for now. It'll take me too long to code up. But let's do, instead of just general likes and dislikes, let's do likes maths. And so we had 1 or true, and oh, I've got to make this an array of size 5, True, true. And do you like maths as well?
No.
Are you sure?
I can tolerate it, but I don't think I like it.
Tolerates doesn't work in C, unfortunately. So I guess we'll put false. And remember, if I'm using an older version of C, I'm going to need to include standard bool.h. Okay, and remember, we want to do our coding practice as well, so I'm going to do n is 5, and then I can put n in here. Likes maths. Okay, bool likes cats. So we had false, false, and
I have a pet cat, so I love
false. Okay, true. So, oh no, I missed some semicolons. So now we've got some information about our people. But there still seems something like a bit ugly about this code. What do you think? Aditi?
If there was a way we could sort of link the name, age, likes, and dislikes to one person, it would be better, probably.
Yeah, what would you call that? Well, in Python, you might call it a dictionary, but what would we call it generally? All of these characteristics make up a class, true, but
Object?
an object is another way of putting it. What kind of object? Starts with a P or an S. Try the one with a P.
I'm not sure.
P-E-R? A person.
Oh.
Not very hard, not a computer sciencey thing, but essentially we're trying to represent what some people would say an object. By that they mean just an entity in the world that's going to have some properties. And we really want in our program a way to represent an abstract data type, so some kind of data type that represents something a little more complicated. Because instance strings, like we get what they are, but they're really a little too simple to capture and conglomerate different pieces of information that we really want to join together. And we can see if we do an example, let's do another example in a minute of a piece of code that really highlights why this sort of coding, the way we've done it right here with lots of different arrays to represent our objects, is probably not ideal. So I'm going to open up another one here called... So what I want to do now is instead of a person, let's pick another P thing, let's do planets. Right? Planets have a whole bunch of attributes associated with them. They've got names, orbits, radiuses, distance, lengths of days. And so I could set up arrays for all of my planets, just like I did for all the people in the class. And then what I can do is I can have a way to print all the different planets. I'll have a special function set up for printing planets. And what print planet will do, it will just index into the arrays and go through from I starting from 0 up to the number of planets we have. It'll go into each of those different arrays and print the attributes for each of the different planets. Now this is a perfectly correct way of doing it, but again we run into this same problem where for some reason our arrays aren't linked, and we want to have a way to link them together so that maybe we don't get confused and we don't accidentally add part of a planet into one array and not add that planet into another array, and then we'll get our indexes mixed up. That seems like a real recipe for trouble. Just like in the same way that when we create a planet, we might want something a little easier than having to index into the array at that location in each of the arrays and make sure that we've actually done it all correctly. So there's got to be something better. There's got to be a better way of doing this. There we go. And this is where we bring into what we call structs in C. Now these are like objects in Python or objects in many other languages, and it's essentially a way of grouping together information that we feel should be similar. So let's look at the basic syntax for one of these structs. And again, it's just going to be a simpler way of doing what we can already do with all our tools before. You can do it in a much more complicated way because you guys are now advanced coders now, but let's try and do it in a simpler way. I told you the class was going to get easier even as we're learning a few new things. So let's open up this struct.c. And C, again, this is the second lecture in a row that I've used that, see how to do it. Okay. So here I have the exact same idea. We're doing the same thing, only this time I'm going to use the C language feature that we call structs. And this is how it works. So I use typedef struct planet T, and this is going to be the syntax. And then inside these curly parentheses, I'm going to put all the different properties that a planet should have. Now you'll notice also that I'm using this other type, pstr_t. Now what is that? Okay, so let's go back up to line 10 and start to unpack this syntax. So typedef is a special word in C that allows us to create our own custom types. Now that type does not have to be a struct. We can just rename an int and call it mySpecialNumber. And then we have a new type in C called mySpecialNumber, which is really just an int. But the reason we have this is to allow us to take a more complicated type and give it a simple to remember name rather than having to type out the full version of the type every time. So in this case, we are creating a character array of 20 characters plus 1 for the null byte at the end. So this is really just a string. And this is going to be a planet str_t, pstr_t. The underscore t is just a way for us to indicate that the kind of variable we're using, it's not really a variable, it's a type name. So that underscore t just indicates, for us, it's good practice, it's not mandatory, but it is a convention that we use to indicate that something is a type. So I've created a custom type. The name of the custom type is pstr_t. And what does that refer to? It refers to a character array of 20 plus 1 letters. Okay, we're all good there. So we're essentially doing the same thing here. We are creating a new type called a planet_t. And what type is a planet_t? What's the more complicated type that we're really hiding under this name? It's a struct. And the details of the struct are within. So it's got 2 strings of size 20 with plus 1 for a null byte. It's got the name, its own name, and which planet it orbits around. Then we have a double for the distance, a double for the mass, a double for the radius. Now this is really the main hard part, is remembering this syntax. And after this, it gets easier. So now when we create one of these planets, we've already told the compiler what a planet_t type is. We have it over there. And then we can just set it like that. Now, unfortunately, this being C, you can only use this syntax to set all the elements in it when you create it. So it's just like arrays. If you've already created an array and then you try and set all the elements at once, that won't work. You'll need to do a loop, or you'll need to access the individual elements. So this special struct syntax, allowing you to populate the entire struct all at once, is for when you create the struct. And so you can see here we've created another planet over there, and we haven't assigned all its details at runtime. Sorry, we haven't assigned all its details in advance. We're going to fill in those details at runtime when the program runs. So now we have the planet prompt again. That's just going to be so the user knows what to enter, and I've put that in a hash define there. And we have our same functions as before, something to print the planet, and something to copy and create a pointer with it. So we'll talk about that more in a second. Okay, so the first thing in our program, in this program, we're going to create a new planet. It's empty, it doesn't have any details inside. In fact, if we were to look inside the memory that our compiler has reserved for us, we'd probably see junk values. Nothing's been set, nothing's there yet. So let's take a look at print planet. This is going to give us, 1 second shot. This is going to give us a little more information about what's inside the planet, our ability to print it, and also give us more information about how we actually use structs. So fortunately, the syntax is really simple and kind of obvious. We use dot syntax to access each of the different properties. So you take the name of the planet or the name of your struct, you add dot, and then the name of the property that you're trying to access of it. So every planet has a name. That's a property of the planet. And then we can simply use that as we would any other variable. So let's mouse over in Visual Studio Code, and it tells me that this is a pstr_t. And if I look up the top, I can see that a pstr_t is really this string array. And so what I can do is I can print as a string the name of the planet and also the name of the planet it orbits, because these were both strings that are inside that struct. Likewise, I can do the same thing with distance, the same thing with its mass, the same thing with its radius. Access each of the properties. Okay, so let's see what this copy struct function does, because we were a little unclear about that. Now, if you remember at the very start here, I'd created a planet, but I hadn't actually populated any of its details. I hadn't said what its name is, what it orbits. And that's what we're going to do in here, in this copy struct function. So firstly, create a new planet. Then print the planet prompt and scanf for all the different things. And you'll notice the locations in which we're putting all of these different things. So I'm putting the name inside the name. Why don't I need the ampersand there? And a string is really a, Jerry? It's an address. And remember, if scanf takes in addresses, and because a string is already an address, we don't need the ampersand in front of the name or in front of orbits. But when we do the other variables that are not locations in memory, then we're going to need to actually get the locations in that memory. And then we're going to return the new planet. Now, you'll notice some subtleties here a bit later if you're paying careful attention. Okay, now let's look at pointer struct. And this is going to take in the address of planet over here. So let's see what happens in that function. Okay, it's going to do something similar. It's going to scanf all of these different things, and then check if it's actually if scanf has successfully read in those 5 values. If it hasn't successfully read in those 5 values, it's going to return an EOF, or that's our equivalent for an error. Otherwise, it's just return 0. So let's give this a run and see if it works and see what happens, and then shall get to your question. Still have the question? No, okay. So let's give it a run. And it's called struct.c. You guys can shout this out and tell me when I'm doing completely silly things. There we go. Okay. Let's make that nice and big. Enter name, orbits, distance, mass, and radius. So Nabia orbits RDT at a distance of 6 seats. Mass, I don't think we're going to answer that one. Let's just put 0. And radius, we'll put 1. Okay. So we can see that Nabia orbits RDT, and it didn't actually need the commas. That was my error. Orbital distance is 7 million kilometers. That seems a little far, but I guess it'll work for today. Mass is 0 kilograms. Radius is, well, if I put 1, in the grand solar scheme of things, 1 is pretty close to 0. But you'll notice one big difference between these two planet routines, in that this one is taking in a pointer to the planet, which actually makes a lot more sense. Because what we ideally want to be doing is we don't want to be copying the entire structure around and copying that structure into the function and then returning a copy of the structure as well, which we can do. It's going to be much more efficient for us just to pass the location in memory at which all the things are stored. And we'll see more of this momentarily. So I'm going to open another file called slowstruct.c, and we're going to compile and run that one. Maybe my numbers were too big, I'm not sure. Okay, so we have a very similar thing again, only this time I'm going to time both the version where I copy the whole struct, where I wasn't using the pointer, and the one where I was. So it's a little hard to see with all of this going on there. Is that still large enough for all of you to read the code? Good. Okay, so the first one, I'm going to do 1 times 10 to the 9 versions where I just copy the struct, and then I'm going to do 1 times 10 to the 9 where I'm using the pointer version, where I'm just passing the address of the struct. And let's see what the difference is in the amount of time it takes. And so to do the timing, I'm going to use some functions available in time.h. And these are not mandatory for you to actually use in the class, but it's a really nice thing to know about to actually go and test your code, and it can give you indications sometimes of when you're doing something really inefficient. So you can either use the time command on the terminal, which I think we saw earlier in the semester, or you can use this kind of structure by building the timing directly into the C program directly. So what I'm going to do, I'm going to capture the start time and the end time. I'm going to subtract the end time from the start time from the end time to give me how many seconds overall. And because the computer doesn't count in seconds, it counts based on the frequency of the CPU, I'm just going to divide that by the speed of the CPU to give me an actual number of seconds. And I'm going to do that for both of them, and then I have some fancy tricks. And I will talk about the fancy tricks in a second. So GCC. So this is for, you can see the results in our two different scenarios. So where we were copying the entire struct, it took 3 seconds to pass the struct directly that many times, but the amount of memory that we actually had to copy from one place to another was 4 billion bytes. Whereas when we were just passing the pointer, it only took 2.6 seconds to do those 1 times 10 to the 9 computations, and look at the difference in the number of bytes we had to pass. That's half an order of magnitude. So we only had to pass 800,000 bytes from one place to the other. Now let's actually look at what I was doing when I called pointer struct and when I called copy struct. So this is a function that takes the struct as an argument, and this is a function that takes a pointer to the struct as an argument. And let's see what those two functions do in this bit of code. Oh, neither of them actually do anything. And this is kind of a bit astounding. It shows us that the difference here can't possibly be because of the contents of the functions. It's just because of the kinds of arguments that the functions are taking. So if the function takes in the structure and not a pointer to the structure, it ends up running much more slowly, because in order to even start, remember that C is passed by value, so it copies the entire structure from the first function, from the main function, into that other function. And that copying process, when we have a structure that has a few fields in it, takes a lot more time and takes a lot more memory. So even without anything actually inside the body of the function, it's taking us a lot longer. So this is really our answer to, should we use structs as arguments to functions? Really, we should be using pointers to structs as arguments to functions. However, given that you're all still new to doing this in C, I would not worry about this too much and just make sure that when you're using structs that it's working, and then if you want, you can worry about this efficiency. So this was not such a problem for our planet struct. Like the difference between 3 seconds and 2.6 seconds, not so bad. And that took us 1 times 10 to the 9 iterations to actually see that difference. But in the real world, not every struct is that small. This is a struct from the Linux kernel, which is part of the operating system code. And this is one struct that contains all the information about a single program currently running on the computer. This is one struct. How many fields does it have? I'm starting to lose count. So you can imagine passing this struct around, and this is many, many times larger than our planet struct, is going to take us a very long time. So long that every time when I run this demo, I inevitably stand here thinking like, surely it's going to end. Surely it's going to end. And it doesn't end. I can keep talking, and I'm going to keep delaying, and I'm going to keep treading water, and finally we're at the end of our struct. So if we're copying that monster struct around, the difference isn't going to be a few bytes or a few seconds. It's going to be really, really substantial. And so that's essentially why we're going to pass around pointers to structs when we start using them significantly in the real world. So just like we create a pointer to any other kind of type in C, we can do the same thing with a struct. But structs do have a fancy bit of syntactical sugar that we're allowed to use with them. And now I'm not sure if I've explained this concept to you. Syntactic sugar is just a fancy way of writing the same thing in C that can be written in 2 different ways. So if we write a and then a dash and a little caret, so I'll write this on my other computer because my nice font has hidden it. But this symbol, if we write that symbol next to the name of a pointer, this is the same as dereferencing the pointer to a struct and then getting the property of it. And why do we do this? Essentially just because we pass around pointers to structs so frequently that it's worth having a special syntax so that we don't have to write kind of that ugly thing, which would get tiring really fast and also probably confusing really fast because it adds additional parentheses. Much better to just have that kind of syntax there that makes it a bit easier for us to access the properties of a struct pointer. Now, there's a bit of a beware here because you have to then keep track of if the thing you're accessing is a struct or a pointer to a struct. If it's just a plain struct, you don't use this syntax. You just use the dot. If it's a pointer to a struct and you want to access one of its properties, that's when you add the special arrow. Any questions up till this point? Yes, Shah. Where did the microphone go?
Well, earlier inside your code, right, you had mentioned that you're using Scanf to enter information into the struct. One of the pieces of information, you didn't use a ampersand in front of it. I don't understand why that is, why you didn't use it.
Sure, let's go back to that for a second. Okay, so let's go down here to when we're reading in the different values. So what we're reading in is we're reading in 2 strings and then 3 floats. Now, what is a string? Shah?
No idea. I know what it is.
Yeah, what is it in C?
It's letters, characters,
Yep.
strung together to make words.
Yep, and so maybe an array. And,
Oh, true.
and what is an array really in C? It's a...
Yeah.
It's a...
Oh, you're asking me.
Yeah, question.
Sorry, we have the wrong person. I have no idea. I'm more clueless right
That's
now.
okay. Okay, so an array is a sequence of bytes in memory, right? And because we have like a set of bytes and it's memory, what do we use when we want to refer to a place in memory?
Sorry, no, the star?
Yeah, it's a pointer, right?
Yeah.
Keep holding the microphone so that we can see when everyone else can hear you. So it's really a pointer. And we know that if we want to modify the value of something in the main function, even when we've passed it to a subroutine, then we need to use pointers, right? That's the point of using a pointer, so that you can change the thing in the main function even once you've passed it away to a subroutine.
Right, got it.
And strings are already pointers. But,
Understood.
yeah, so that's good. So we don't need any special things because they're already pointers, they're already addresses. But these 3 values, they're just doubles, right? They're normal numbers. And those aren't pointers. And so if we want to have the subroutine modify them, then we're going to need to pass the subroutine an address. And the way we turn a variable and get its address is that ampersand symbol. So for the things that are already addresses, because they're strings and strings are really just pointers, we don't need an ampersand. For the things that are just normal variables and aren't pointers, then we do need the ampersand.
So for the normal variables, right, when you put the ampersand in front of it, are you editing the content of like planet radians, or are you editing its address itself?
So the idea is you're copying the address that you have inside the main function, and you're giving that address to Scanf. And then what Scanf can do is it can go and say, I've got this address. Inside that address, I'm going to fill it with some new data.
Right, okay.
So Scanf could try and change the address, but that change is just a change on the copy of the address. What Scanf really wants to do is it wants to take that address, dereference it, go to the place pointed to by it, and put some new contents there. And that's what it's essentially doing when the user types in data. Scanf says, here's the user's data. I've got a pointer. I'm going to go to that place pointed to by the pointer and put the user's data in that location. All good?
Yes, thanks.
Okay, any other questions before we move on? Finn.
When you put the ampersand in front of the planet arrow radius, for example,
Yep.
is it doing that arrow operator first or the ampersand first?
Yeah, so you could write that as
It's
that
like
way.
that. Okay.
Yeah.
I was misreading it. That's all.
So nothing particularly fancy there. Okay. Okay, so we have a couple of ways of creating our struct pointers. Now, the first one is to just create our student as normal, create a normal struct. So this tells the compiler, create the memory for the struct, populate it, and then once we've already created it, then we can get the address of the location that we've created. So at this point, this is just the same as the kind of thing you would do for any other variable. So if you were doing this for an integer, you can create an integer variable, put some value in it, and then get the address of it. So nothing particularly new there. And then what we can do is we can, if we have this function print student name that takes in a pointer to a student, we could give it ampersand kwaku. Because kwaku is our student. It's a normal struct. It's not a pointer to a struct. And so to convert it into a pointer, we would use the ampersand. So that's method 1, pretty straightforward. Here is method 2. So kind of the same as before, only this time, instead of using the normal construction that we've always been using to tell the compiler to tell the computer to set aside some memory for us, we're going to do something new. We are going to explicitly tell the computer that we want memory. We're going to tell it how much memory we want, and we're going to tell it what kind of thing that memory could be used for. And that's this line of code all the way up there, using this special function called Malloc. Malloc is essentially our way of telling the computer, please give us some memory, and if we're asking the computer for memory, what will it probably give back to us? Say a bit louder. So hopefully it won't give us a segfault. Hopefully it will give us memory. What type do we use to refer to memory? A pointer. Who said that? Finn. Yeah, it'll give us a pointer. Now, does the computer automatically know what type our memory is going to be? No. So by default, the type of pointer that it's going to give us is a void star, a pointer to an unknown type. And the reason we're using void is because it's really just a block of memory. You can fill whatever you like in that block of memory once you've been given it. And so it's going to be the programmer's job to determine and define what type that pointer is eventually going to be cast to, what type it's going to become. So Malloc is what allows us to ask our operating system for some memory without explicitly having to ask for a particular variable. And then once we have that chunk of memory, we can do with it as we please. But as Toby says, once you have this very powerful tool in your hands, it is quite likely that you are going to start running into segfaults more frequently, particularly as a more junior programmer, because you're playing with raw memory. If you step outside the memory you've been given, you'll get a... If you touch memory belonging to some other program, you'll get a... Exactly. So lots and lots of different ways. If you accidentally forget to give yourself the memory, or you free back, if you return the memory to the operating system and then try to use it again, you'll get a segfault. So this is segfaults all over the place, which is why for many of the assessments that we're going to give you, at least at the start, we'll give you the option of whether you want to take the easier route and use like structs instead of pointers to structs and allocate the memory that way, or whether you're going to use Malloc and actually give yourself the full toolkit. And while doing it this way is probably going to be much, much more efficient, it is a little bit harder, so we do understand that. So this is the man page for Malloc, and if you remember, the man pages were the way that I could get my operating system to give me information about some of the built-in functions. So let's just try it on my other computer here. I'm going to clear the screen, and then I will do man malloc. And you can see I have a whole bunch of functions in this particular page, all of which are about managing requests for memory. And all of them return void star, and they're inside this header file, stdlib.h, standard lib. Let's just read the first page, the first part of it. The malloc, etc. functions allocate memory, blah, 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 blah. The malloc function allocates size bytes of memory and returns a pointer to the allocated memory. So let's look at malloc. Malloc takes in a size argument, and you'll notice here that we're using this convention again, where there's a particular type, and because it's a kind of a special type, rather than int or char, it has a suffix of _t just to indicate, to remind us that it is a type and not the name of a variable. Because you might want to call a variable size, and so having the _t just means, okay, we're very clear that's a custom type. Now, what is size t? Size t is going to be the unit in which we measure memory. Now, you will remember that some computers only were like 32-bit or only were 16-bit. And so if you wanted to ask for an amount of memory, you'd only need the size of your request could at most be a 32-bit integer or a 16-bit integer. And so this size t type is a type that depends on the type of computer you're running. If you're on a 16-bit computer, it might only be a 16-bit type, because the computer knows that you can't ask for a chunk of memory larger than 16 bits because it's only a 16-bit computer. So that's what a size t is. It's a special value that's declared inside. It's like a hash define, kind of similar, declared in standard lib.h, that is going to tell you what type that size request can actually be. And so you don't have to worry about it. You can just type in the number you want, and it will automatically convert it to a size t, assuming that it is within the size permissible. Okay, let's look at one of the other ones for the time being. This is the free function. The free function deallocates the memory pointed to by pointer. If pointer is a null pointer, no operation is performed. So there's like another trap for us. No operation is performed if you try and free something, you've already set to 0. But it also, you'll notice something's missing here. It doesn't set the pointer to 0. So you can have a pointer that points to a specific address, say it points to address 55, and you've already freed it. That means you've already returned it to the operating system, but the pointer still has that address sitting there. And so if you're not careful and you try and use address 55 after you've freed it, what do you get? Segfault. And this is where the real trouble begins, managing this balance between requesting memory, giving it back to the operating system, and remembering when that you already have given it back, and remembering for every bit of memory that you've taken out to return it at some point. And we'll talk a little bit more about this in a minute. So this is the picture of our computer's memory that we've now seen a number of times before. And up until now, where have most of our variables been? Yeah, the stack up the top there. Right? Automatic variables, callers, return address, and it goes down. So we start at higher memory addresses, and we go to lower memory addresses in the stack. Now what we're going to do is we're going to start using the heap. That's this segment of memory over here. And when you call malloc, the computer is going to find a chunk of memory somewhere in the heap and give it to you. And you'll notice one kind of interesting thing here is that the stack and the heap grow in opposite directions. So every time you ask for something from the heap, you'll get a larger and larger memory address. If you've asked for 5 things, the 5th thing is going to have probably a larger memory address than the 4th thing, not accounting for the fact that you might have freed stuff in the middle. But in general, the more you ask for, the larger the heap gets, and will get higher and higher addresses. The stack, on the other hand, say you've made like 30 stack variables, the 30th stack variable is going to be at a lower address than the first stack variable. And now you can imagine that this might end badly. If you have too many stack variables and you keep adding things to the heap, you might get a collision between them, and then you'll likely get a, quite possibly, but not guaranteed. There are some other things that can happen. So that time, not 100% true. So malloc allocates memory on the heap, and malloc is going to give back a void star, a pointer to the memory we're allocated. And for every time that we malloc some memory, we have to remember at some point, doesn't have to be right away, doesn't even have to be in the same function, but we have to free it. Now this gets really tricky fast, because let's say you have one function that's allocating the memory, and that gets used throughout the rest of the program, and then sometime later you're finished with that memory that you've created, but it's in a different function. You need to have some way to keep track of all the different chunks of memory you've allocated at different times, even when they're in different functions. And this is one of the reasons why a lot of modern programmers prefer not to use C, is because all of this management has to be done manually. And this can lead to something we call a memory leak. So who here has used a web browser before? Put your hands up if you've used a web browser and after a while your computer starts to get really slow. Okay, put your hand up really high so we can see and we can look around. So I would say that's like 80 to 90% of you or so have had that experience before. And one of the most common reasons why this occurs is because someone has forgotten somewhere in the web browser to add a free, or in the equivalent in whatever language the web browser is written in. And what this means is over time, the web browser is going to keep allocating new memory. Say you visit a new web page, it allocates some memory for that. You watch a little cool animation in the browser, it takes up some memory for that in the computer's RAM. And over time, you keep adding things, but there's one category of things that the programmer has forgotten to free. And so your web browser starts taking up more and more and more and more memory until you've actually exceeded the amount of memory available in your computer. Now, does anyone have an idea what might happen then? It's not a seg fault. Jack. So Jack says your computer just crashes. That is one possible option, but that would probably not be great operating system design if you'd done it that way. The operating system could kill the process. That's another common way of dealing with it, but it's actually not the most common. And that's okay. I wouldn't necessarily expect you to know. What actually happens is instead of using RAM for your computer's temporary memory, it actually starts swapping some of the memory in RAM out to your hard drive and then using the space that's cleared for the thing it needs most recently. And then when it needs the thing it's put on the hard drive, it goes back to the hard drive and takes the thing from the hard drive and puts that back in the computer's memory and then keeps doing this swapping in and out and in and out and in and out. Now, why might this be a bad thing? And I'll take someone from the audience. Where is Michael? Put your hand up. There you are. Couldn't find you for a second. I'll pass this back to Michael. Okay, why might this not be what we want? Okay, so when the computer... so what we had is we had a program that had been allocating lots and lots of memory, and had allocated more memory than the computer actually had RAM for. So what was happening is every time it needed a bit more memory, it would take something that was in its RAM already and put that on the hard drive, use the memory, use the freed up space, and then it would take the new stuff there and put that on the hard drive and take the bit from the hard drive back and put it in the RAM. What's the problem? Why might we not want that to happen frequently?
It's a lot slower.
It's a lot slower. So tell me a little more about that.
Well, it takes time for... Well, it's not the random access memory, so
Yeah.
it's not... The hard drive is not specifically made to... It's not designed to do that process quickly enough.
Okay, so have you ever looked inside a computer before?
Maybe some pictures only.
Okay, so how close is the RAM to the CPU?
There are two different components.
Yeah, they're different components, but like, is the RAM close to the CPU or are the hard drives close to the CPU?
The RAM.
Yeah, the RAM is much closer. The RAM typically has a very direct link, and the hard drives are often located physically further away. Now, physical distance is not the be-all and end-all, but that should give you a little bit of an indication about what the design kind of thinking here is. Now, Michael's very right. The RAM is designed to be ultra-fast and to have things that the CPU needs all the time, whereas the hard drive is for longer-term storage of data, for which it doesn't matter so much if it's slow. So I'll take the microphone back, and we'll turn that off. Thank you very much, everyone. So essentially, this process of rapidly having to swap things in and out over and over is what we call thrashing. And it's really bad because the hard drive is about an order of magnitude slower than the RAM. And so every operation for which you need to access memory starts taking an order of magnitude longer, and all your programs start to become very, very slow. So this is why managing your memory is such an important feature, not only of basic programming, but also of writing a good operating system. You have to decide between how you're going to handle when you're out of memory. So the world's oldest computers, when they were first created, probably would have just crashed. Was that Jack's suggestion? Yeah, just crash. Some other computers, before we came up with this notion of memory swapping, might have given you an out-of-memory error and killed the program. And that can still happen. You can turn off swapping on your computer, and then probably all your laptops just become incredibly slow when they start to swap in and out. Okay. So we also have one new operator to help us deal with all of these operations around memory. And this one is going to be pretty useful. This is the Sizeof operator. And you would have seen this a few seconds ago in the demo by which I used Malloc for the first time. So here we go. In my first Malloc demo, you can see I've used Sizeof over there. And this is an operator, just like plus, minus, divided by. Even though I've kind of put parentheses here to make it look like a function, it's really an operator. It's a basic inbuilt part of the language that will tell us the size of a type. So here it's going to tell us how many bytes do you need in order to make room for a full student T, which is the type of a student, and you can have as many different fields in there as you like, and Sizeof will tell you how many bytes you need. So you could do size of an int, and how big is an int on a normal computer now? Say a bit louder. 64 bits, or 4 bytes is on an older computer and 8 bytes on a more modern computer. And so that's what Sizeof will return depending on the particular computer on which we are running. There we go. So Sizeof produces an unsigned integer, so that means an integer that can only be positive, because you can't have a type with a negative sign. Again, the details of exactly how this is going to work is dependent on the architecture of your computer, but generally this is going to be a safe assumption, at least for your purposes. So there is one catch. It's a trap! As Admiral Akbar is letting us know, Sizeof is not going to work to give us the size of arrays as a general technique. There are some cases where it will work, but I strongly recommend not using Sizeof to figure out the size of an array. Rather, keep that as a variable separately, because as soon as your array turns into a pointer, so like when you start passing it into functions, it's not going to work, and you're going to get the size of a pointer back rather than like the number of bytes actually taken up by the array. So that is definitely not what we want. And with that, let's take a break until 2:48. And then we'll come back and talk a little more about using all of these structs and memory management and all the exciting things we can do with it. All right, everyone, we are back. Hope you had a few minutes to recover. But today has been relatively gentle so far, so let's kind of keep that pace going forward. And then tomorrow we're going to start hopefully talking about some more advanced things that we can do with all of these techniques. Yeah, that is me too, taking a bit of a nap here at the front. So one other interesting and useful thing that we can do with structs is we can have structs inside of structs inside of structs, just like our lovely Matryoshka dolls here. And so here is an example of the task struct, this like ultra long struct that I showed you before. And you can see that it has structs inside of it. So it has an unsigned int called saveState. There's another unsigned int called __state. These names are a bit confusing, but it also has a struct inside it called threadInfo. And if we look inside the same file in which this big task struct was defined, we can also find the threadInfo struct. So we've embedded a struct within our struct. Now, let's go back to Nabia. Where did my microphone go? Is it sitting somewhere here? Yes. Wait, you didn't have a pet. Aditi had a pet. Aditi, sorry. I keep doing that. It's just an old friend's name. So remind me, oh, this is off. So let's switch that back on. There we go. Okay. Aditi, remind me the facts that you told us about yourself. One of them is going to be particularly relevant in a second.
I don't like math, and
Yeah.
I have a pet.
Have a pet. Okay, that was the one I wanted. Tell us a bit more.
She's a tabby cat.
Okay.
Her name is Mizu, and she's a year old.
Okay, we've got 3 pieces of information. How would we represent that in our program?
You could create a struct for Mizu.
And what will we call it? What type is it?
Cat? Pet?
So let's make it a cat _t, just so we're
Yeah.
sticking to convention.
Yeah.
And to keep track of our other friends in the class, like Maria and Nabia, what kind of struct were we using?
We were using student, right? Or
Yeah, student
person.
_t or person _t.
Yeah.
And how do we then keep track of the connection between student _t and pet _t?
I'm not sure.
So maybe every student _t could have a field inside of it that is an array of
Characters?
it could have, no, well, we just said we need a connection between 2 things, right?
Yeah.
You've got a cat. These 2 didn't have a cat. And they're
a
person
Boolean
T's.
array. Or like has pet
So
Could be
we
either
could have an
true or
array of has pet, but really you gave us all this information about your pet. We want to store all the details. Is the pet a tabby? Is it, what's the name? Is it Mizu? Is it Foi Foi or something like that? I don't know. So what are we going to do? We'll have an array of...
I'm still not sure, sorry.
So you said we have a type, pet T.
Yeah,
And a single person, can they have multiple pets or only one pet?
multiple.
Multiple pets. So that probably means we need an array, right?
Yeah,
To store multiple things of the same kind. And we're going to store an array of what type? Like, what are we going to put in the array?
strings.
Not strings, because a string is only like the name of the pet.
Oh, you'll have an array of the pet struct.
An array of the pets. So we have a pet T type, and for every person is going to have an array inside their struct, an array of pet Ts. Now, you'll remember also something about a warning against making our structs really big. So what might we want to do instead of having a built-in array of size 10 of pets for every person?
We could allocate some memory.
We could have a pointer to the place where all their pets are, and then if they don't have any pets, we might not need to allocate any memory, and then if they do have pets, we might decide that we do want that allocated. So let's sketch out how this would look, really roughly, not in a full program of just what this might look like. So let's do our typedef struct. Oh. And then person underscore T. And so we had, what was the first thing that we knew about a person?
Name.
Name, and so this is what type?
String, so char star name.
Char star name. Yep.
Int age.
Int age.
Then there was
So let's skip some of the other stuff. Let's go right to what we were just talking about.
Yeah, pets.
Okay. And what type is that?
Pets underscore T.
Yeah, pet T. And we can call that pets. Right? And we said maybe we'd make that a pointer, or maybe we'd make that an array. We could do it either way depending on how fancy we want to get. But now we've run into a problem. What's our problem?
We have to define pet underscore T.
Yeah, we have to define a pet T. Okay, what am I going to write?
Char star pet underscore name.
Yeah, so we could just do name. We don't need pet name.
And again, int age. Char star breed. Yeah, that's all I can think of.
Well, probably.
Oh yeah, and species.
So I would say probably these last two fields are particularly important, or for those of you who have pet spiders, or a dog, honestly. So this gives you an idea of how we might start to structure things. But if I was to compile this, now let's save this as cats.c. And let's try and compile it. And it's not going to work, and we'll see why in a second, but that's okay. Okay, first thing is I'm missing a semicolon, and I haven't actually called this a pet underscore T, so that's bad on me. Okay, unknown type bool. We're getting through our errors. There we go. Unknown type name, pet underscore T. So Aditi, why might it still be unhappy with us? Or you can pass on the microphone if you want behind you.
Would you have to define the pet type before you
Yes, it's the same thing we had with, the same issue we had what?
Functions.
Yeah, with functions. So we've used pet T, but our compiler doesn't know what pet T is. So what do we do for functions to solve this problem?
You define the prototype at the beginning.
Yeah, so it turns out we can also do the same thing with structs. So we will see this in a second. Let me open up. There we go. So one way of solving the problem is to very carefully order our structs so that they are in an order like that, and now it'll probably be okay. And now it's unhappy because I haven't written a main function. So let's do that quickly just to prove that it works. So void main void nothing inside it, and it should compile. Yeah, it's complaining because the type of main isn't int, because it's being a good compiler. There we go. Okay, now compiled without error. And so one way of solving this problem is to put the structs in order, and the other way is to prototype the name of the struct as well, using the typedef command earlier, although you don't need to include the full definition at this point. So let's take a look at another way that I might do this, just as one more quick example of why you might actually want to nest structs and how this is used in practice. So this is a nested structure example I've got of more student t's. So here I have fullname.t, and you might have 3 different things inside full name. You have your given name, any other names, and your family name. And each of these are name strs that I've declared up there. So you can see I've used that type, that custom type, inside this struct. Then I have a date t for year, month, and day. I have a subject t for all the subjects that they might want to take, and a student t. So this is really the complicated one. Inside a student t, you have subject t, all the different subjects they're taking. You have a full name t, a date of birth, a student number, and number of subjects. Now, Aditi, do you want to pass the microphone back? What was your name?
Kevin.
Caleb?
Kevin.
Kevin, sorry, hard to hear from down here. Why do I have this n subjects over here? Why is this variable important?
Could it define an array of which subjects you're taking?
So I've already got that subjects array, and I've got it set to max subjects. Why do I need n subjects as well? I could rename this to make it a bit clearer. It gets a little long, but why do I need that variable at all?
No, I'm not sure.
So remember, if I have an array that is maximum max subjects, that doesn't actually mean that it's full. So I could say the maximum number of students, subjects that a student at Melbourne Uni can take is 5. Most students don't take 5, some students take 4, and some students take 3 a semester. But for a given student, we need to know how full this array is so that we don't start reading outside the end of the array. So in this sense, declaring these 2 variables together and putting them inside the same struct allows us to pass them to functions together. So you know how all this time now you've been having functions with 2 arguments. One argument is n and one argument is the array. Well, sometimes if you use structs, you can avoid having to do that. You can just pass a single struct which has both of those pieces of information together. Now, I will say that if all the function does is operate on the array and the size of the array, then it is more standard to pass both and not create a special struct just to pass them together. But in other programming languages, this is essentially what's happening behind the scenes, is you have code that's passing these 2 pieces of details, these 2 details together. So when you use Java in subsequent subjects, it's not that Java's arrays are special and the computer actually knows how long they are. It's just that behind the scenes, Java is really using this kind of notion of having a struct to pass the 2 pieces of information together at the same time. So unfortunately, structs are not magical and do not solve all our problems. They come with a number of limitations. And probably the biggest one that all of you are likely to run up to, and a common mistake that many of you might make, is trying to compare structs directly. So for example, we know that when the first time we create a struct, we're allowed to set the elements all at once. Okay, so these first 2 lines are fine. But what about the next 2? Here we're trying, that's an equals equals sign, by the way. That's just a long equals in that font. I'll have to change that for future years. But if we try compare if 2 structs are equal, it doesn't work. And if we try and check if one struct is greater than or less than the other struct, it also doesn't work. Now, it was Kevin, right? Still on?
Yes.
Okay. Why can't I compare 2 structs? So let's go back to Aditi's cats. Why can't I compare cat1 and cat2? Do you have 2 cats? Oh, okay. Let's give you a new, I'm giving you another cat for today. It's near identical to the first one. Why can't I compare the 2 cats? This is for Kevin.
I have no idea.
Well, how would you compare cats?
Just look at them.
And then what would you do?
I don't know.
Okay. Do you want to pass it maybe one row back? What was your name? Oh, okay. Whoever wants can take it. It's an easy question. How do you compare a cat?
You just look at them, but if they're 2 different cats, then they're just 2 different cats, and not the...
Yeah, they're just 2 different cats. So it's kind of a weird question to ask, like, how do you compare 2 cats? What does it mean for 2 cats to be equal? So to define that, you have to say, okay, maybe it's if they both have the same name. So 2 cats named Sushi are equivalent. Or 2 cats that are the same age are equivalent. Or 2 cats are the same if they have the same number of spots, the same name, and live at the same address. So really, this is why you can't compare structs, because it's unclear a priori what it actually means by comparison. So you can write your own function that is like compare number of spots. And that'll tell you which, you can give it 2 arguments, cat1 and cat2, and it will tell you which cat has more spots. Or you could even ask for equality. Do both cats have same number of spots could be your function. But a priori, because it doesn't make sense to do these comparisons, C doesn't automatically make the decision for you of how to check for equality. So even if all the fields in the 2 cats are the same, because this notion of cat comparison doesn't really make sense, C doesn't let us compare structs directly. And so there are a few ways in which structs are like arrays that we've used for a similar purpose, and some ways in which they are not. And so in the textbook, you'll find this nice diagram which you can use as a reminder of all the different ways in which, all these nice ways in which arrays and structs are similar, in which you can do things the same way you do for both, and other ways in which they're a bit different. So for a struct, you can do some direct assignment. You can compare 2 arrays as pointers, so you can compare if their addresses are equal. You can't do the same thing with structs, and so on and so forth, as you can see. And really, what we've achieved in this class so far is exactly what we were talking about at the very first minute when we were introducing Barbara Liskov. We have introduced another form of abstraction over data. So just like we could use functions to break up our big piece of execution into bite-sized discrete chunks that made sense, so we could break up a problem such as finding the next prime into like is prime and next prime, we can also do the same things with data. Instead of having memory that's all contiguous and that we don't have any definition for, we can start to impose structure on our data and build types out of types out of types out of types, or bigger functions out of smaller functions out of smaller functions and smaller functions, and bring order out of all the chaos of computing. So just a little bit more on Malloc. I wanted to give you a pattern that you can use for practicing to use Malloc in the correct way. So this is what a good bit of code that uses Malloc more or less looks like. So it starts off by creating a pointer of whatever type that you wanted to create. So we have our type T. It doesn't really matter what type it is. It could be a student T, it could be a pet T, whatever the type is. So we've created our pointer. The next thing we have to do is figure out how many elements we want our pointer to hold. So remember that arrays are really just memory, and it's memory that has enough room for X items of the same type, or N items of the same type. So what that line there is just saying, figure out how many items of the same type you need. Is it just 1? Do you need 5 items of the same type? How much memory do you need? Then what you do is you do n times size of that pointer. So you can either do the size of the type or the size of one of the objects of the type. That's kind of equivalent. And it doesn't really matter which you use, because dereferencing a pointer of that type gives you the actual object itself, and you can get the size of the actual object. So that's the same thing as putting type T in there. So I want n items of that type, put that inside Malloc to make the request, and then on the other side there, you'll see that I'm actually converting that void star pointer, because remember, Malloc gives us back a void star. It doesn't know what type of memory this is going to be used for. And so we're actually converting it into a pointer of a type t. And that's what that line is doing. Then we want to check if malloc actually succeeded. So if malloc fails, that pointer is still going to be 0. And so actually, what we probably should have done is set that to be 0 in the first place. However, if you read the manual for malloc carefully, you'll see that if it fails, the return value should be 0. And so that pointer will actually be set to 0, and we don't really need that allocation. So error, no memory available. If that's failed, we don't know the details of why malloc has failed. That's up to the operating system. But if we're not able to get memory, that indicates that something really bad is happening, and we should probably just quit the whole program. You can also use Assert, which you guys have seen Assert already in the class? Yes, no? I see some head shakes. Okay, I see some no's. I see one very vigorous head shake. Yes, for sure? No, woman all the way in the back in the glasses. Okay, given that we seem to have collectively have amnesia, where's the microphone gone? Let's pass it back and we can have a bit of a reminder on what Assert was. Thanks for volunteering. And can we have your name as well?
My name is Para.
Para?
Para. Pratiksha.
Pratiksha?
Yeah.
Okay, that's easier actually. Easier to hear, at least from the front. What does Assert do?
It asserts if the value exists or if it is meant to be the type that it's meant to be, and if it doesn't, the function fails.
Almost. So what do we mean? What do you mean when it fails? What happens if an assert fails?
The program crashes.
Yeah, the program crashes. So assert is a way for us to make absolutely sure that the value inside is true. So it contains a non-zero value. If it contains a 0 value, then the program crashes. Thank you very much. So our assert there, which you definitely have seen assert somewhere in this class, is just a special command that we have inside assert.h, which will crash the program if whatever in there turns out to be 0 and false in this case. And then once we have our pointer, this is where our malloc is over, and then we can actually do stuff with it. And then at the end, we've got to remember to free it and set the pointer back to null. So remember, these last two really should come together. This is indented a little bit the wrong way. I'll fix it. So you'll see that not only have we freed it, but we've also set the pointer to null. The reason we do this is because if the pointer still has a non-zero value for it, but points to memory that we've already given back, the chances that we misuse it are really, really high. Yes, Jack. Pratiksha, do you want to pass the microphone forward? Thank you.
Is there a reason why it's not just assigned null in the free function?
That is a really good question.
Like if it's just going to cause issues most of the time.
I actually don't know the answer to that one. I'll have to get back to you on it. I suspect the type of answer it's going to be is going to come down to like low-level details about the way operating systems work, but I don't actually remember that off the top of my head. And I don't think I've even looked into it once. So we'll get back to you on that one. Okay, so let's see some examples of this. So here's an instance in which I have created a new type. In this case, it's going to be a plain t. And my plain t is going to have a nested struct within it, and that is going to be plain seats. So what I'm going to do is I'm going to allocate some memory for the plain seats, for seat t's. And how many seat t's am I going to create? Well, I want to know how many seats this individual plane has. So this is my plain variable. But this is just generally to indicate the way that you might access one of the elements of the larger type, of the larger struct, and then use it to set one of the pointers inside the struct. But now let's say there is an announcement that there is a change in plane. So all the passengers on the old plane are going to have to move into a new plane. How would we represent this in our C code? So one thing you might be tempted to do is just create a new plane and use the same seat variable as before. So the problem that we have here is this new plane might be different, and it might actually require a different number of seats, even though we still want to use all the memory that was in the previous seat structure. So what we really have to try and do is we've got to figure out some way of getting all those old passengers in their old seats onto the seats in the new plane, and then hopefully fill up those extra seats as well. So we have a few options of how to do this, and I'd like to get some ideas from the audience. Jack, you've still got the microphone, right? What was your name?
My name's Michael.
Michael, okay, Michael number 2 for today. So what is one way that we could transfer the passenger information over? From our old plane seats 1 or plane seats to the new plane?
I think I can iterate through it.
Yeah, so we could iterate through it. So we'll get to that one in a second, but the most obvious thing we can do is just use any extra seats that are left over in the original array. But given that we were pretty careful about mallocing the exact number, this might not be a great solution for us. So if we try and use extra memory that's in the computer's memory beyond that which was available to us by malloc, what do you think will happen? So let's say we malloced 175 seats, and now I'm accessing seat 245.
An error? An error.
What kind of error?
Like fault?
Okay, so now we have option 1, which was your better idea. And repeat it for us, what was your idea?
Iterate through every sheet and copy it to a new one.
So this was the idea. We could create space, a new variable for the new seats, and we'll use malloc and figure out how many seats are in the new plane. And then what we do is we iterate through all of the old seats, and we copy the passenger details from the old seat into the new seat. So plane seats old becomes plane seats new, assuming that we have written some other function, copy seat, that has all that logic. So that was a really good idea, and that's essentially what we're going to do a lot of the time. We do have one other option though, and this is a function called realloc. So I'm going to go back to my other computer and pull up my man page for malloc again. And you'll see that there's this function here, realloc, that takes 2 variables, and let's look into what the man page says. Realloc tries to change the size of an already allocated memory block of an allocation pointer 2 by pointer to size and returns the pointer back. If there is not enough room, realloc creates a new allocation entirely, copies as much of the old data as will fit, frees the old allocation, and returns a pointer to the allocated memory. If pointer is null, it's just the same as malloc. Okay, and then you can read the rest later. So this gives us a powerful tool that we can use to simplify some of this legwork that we were doing through the iterative method. And this is just because this is an operation that people want to do really, really frequently, is to take everything that was in an old smaller chunk and make it into a bigger chunk. And the details there just said, well, if there's actually room in the computer's memory, allocate that memory that's immediately after the old block. So you could actually do this if you used realloc first, and it did give you that memory. You'd be able to access those spaces. However, if that block isn't available, realloc will make sure that you get a new block that is large enough. And so all that code that we had in the prior slide, we could just do with this one line of code here. Which gives us another question. How much should we grow our allocations? I mean, if we're always anticipating that we might need to do this somewhere down the line, why don't we just allocate more memory? Michael, what do you think? Why don't I just allocate a larger plane to begin with?
I think it's not efficient, I think.
Yeah, it's really inefficient. And then that leaves us with the question of, okay, so every time a passenger gets on the plane, why don't we just be super efficient, start with an allocation of only 1 seat, and then grow by 1 seat every time a passenger gets on board? Why isn't that a good idea? We're being really memory efficient.
I'm not sure.
Well, what was your suggestion for how, let's pretend we didn't have realloc. What was your suggestion of what to do?
My suggestion was like to iterate through every passenger and copy it to the new one.
Okay, so let's say we have 1 passenger on board, and we've allocated space for 1 passenger. Now passenger 2 comes on board, so we copy the data from
the second passenger.
Yeah, we copy the data from passenger 1. Okay, now we've got 2 passengers on board. We have room for 2 passengers. Okay, 3rd passenger comes on board. What do?
Copy the third one.
Well, we have to copy the first one and the second one into the space that we've just made that now has room for 3. So we copy the first one, the second one, and now we have room for 3. Okay, 4th passenger comes on board. We now allocate memory for 4. We copy 1, we copy 2, we copy 3, and put the 4th in. 5th passenger comes on board. We now allocate. You can see where this process is going really quickly. Doing these allocations gets very expensive because copying things around in computers' memory isn't free. So it actually turns out that you have to be very careful with how much you're doing reallocs and how much you're allocating memory ahead of time to trade off between the amount of space that you're wasting and the amount of time that you're wasting copying things when you could have allocated memory ahead of time. So mostly what we tend to do as computer scientists, we like powers of 2 for all kinds of reasons. They tend to be efficiently implemented in hardware. So what we'll do is we'll always double the amount of memory we've allocated. And also it's quite typical to do memory allocations in blocks of power of 2 when it's appropriate. So Realloc is expensive, and it's often better to just waste a little bit of extra memory but not continuously do the reallocations. So what is the value of plain seats after that code runs? You don't have to give an exact answer, just give a general answer.
So it's the value we have assigned before, which we have defined the amount of seats we were going to give to that array?
Not quite. Does anyone know? What's the value of plain seats after this runs? Yeah. It's a pointer to some place in memory. And I've forgotten your name last lecture as well, so you have to remind me now. Rex. This keeps happening. I don't know why. Sorry, Rex. Okay, so it's going to be a pointer. And now, Rex, do you want to answer what the value of plain seats is after this code runs? Will it be null? Tyson?
It should be 0, right?
It would be nice if it was 0, but we've been through this discussion a few times. We remember that free, this was Jack's question, free doesn't actually set it to null. And this is a really big trap that we always forget, is that free doesn't actually, it doesn't take the pointer and make it 0. What it does is it gives the operating system back the memory, which is different from changing the variable. It doesn't change the variable. What it does is it changes which memory we have permission to access. So that is a bit of a trick. So it's a trap. The pointer still contains the address. And so if we try and access it, we would get a segfault. Yes, Toby? That is a good point. The operating system, so it doesn't actually erase it, it doesn't 0 it. And so if you're writing something that's a very sensitive security application, you typically do want to overwrite that memory directly, and that's called a secure erase. It's not easy for another program to just get access to that, but there are problems with that. So the moral of the story here is after you free a pointer, don't forget to actually set it to null. Not so bad. So there are a few tips that I'll give you for managing your mallocs. The first is to always check if malloc succeeded. The second is don't assume you know the size of a type, so don't just assume that an integer is 4 bytes. 1 minute, because the computer that you're running on might have differently sized types. Don't forget to free. Don't forget to then set the pointer to null. And the return type of malloc is void star, so always remember to cast it. Yes?
If we did set the pointer to null and then tried to call it,
Dereference it.
we would get a segfault anyway, right?
Yep.
So, like, if we're going to get a segfault regardless of, like, what's the point of setting it?
Because then you can check if it's been already freed or not by setting it to null. Because then you know you've kept track of it, I've already freed this memory. And that will avoid you running into a segfault. And so now we have a couple of demos. Give me a second. I'm just trying to double check what we're going to do the rest of today. So we have a few very quick demos about this stuff, and then we might even get out a few minutes early. We'll see. Okay, so here I'm just showing you what happens if you call Sizeof on a variety of different types. So the first thing we're going to do, we want the size of a character, the size of an int, the size of a float, the size of a double, and then what we have is we've got an array of 10 doubles. We're going to see what the result is from the size of the array variable itself, the size of the first element of the array, remember that's what happens when you dereference an array, the size of p, which is a string, and the size of star p, which is the first character in the string, if you're paying close attention. So let's compile this one. And we see our results here. So size of a character is 1 byte, makes sense. Size of an int is 4 bytes on this computer. Size of a float is 4. Size of a double is 8 bytes. And then this is where we get a little interesting. The size of the array is 80. Now that would be 8 times 10 because it's got 10 doubles. But didn't I tell you before to avoid using Sizeof on arrays? Well, it is true. You can use Sizeof on arrays in some scenarios. If you're inside the same function where you've declared the array and you explicitly allocated how many the number of items in the array, this will work. The reason I told you not to use Sizeof on arrays is not because it never works, it's because it only works sometimes. So if we were now to have another function called printArray, and I were to pass the value, if I were then to pass the argument a into printArray, Sizeof would stop working because inside the details of the compiler, it would have converted what it knows about the array and stripped away some of that information, and now it's just passing a plain pointer. Now, even though we might know as the programmer that that pointer is being passed as an array, and so on the other side, we can still treat it as an array, we've lost some information in the process, and so Sizeof won't work anymore. Okay, then we do size of star A. That's really referring to the first element in that array, so that'll give us a double of size 8. Size of P, so that's this char star, is going to be 8. Why is it 8 here? Who's got the microphone? It's Tissan, right? You want to pass it over to Aiden, was? Why is size of P 8?
Because that's the size of the pointer?
Yeah, it's the size of a pointer. So what we've actually done here is instead of asking for the size of the string overall, what we've gone and done is we've actually asked what is the size of this char star. It's really storing an address in memory, and so when we ask how many bytes do we need to store an address in memory on this computer, the answer is 8. And then if we do size of star p, well, we're actually asking the size of the first element, and the size of the first element is the size of a character, so we just get 1. And so you can see if you're not careful with your what you're trying to get the size of, you can end up with a result that might confuse you. And I keep forgetting your name as well. Isaac.
When you said that the size of A will stop working, does that mean that the operator won't do anything, or does it mean
It'll give you the size of a pointer, because it now thinks that it's just a pointer. So just like when we do size of P gives you 8, you'd also get 8. But give it a try. I think there's, who was it? Someone, Jerry, were you asking about something similar? Someone who came down to the front before. It was Finn. Said that there is an exercise on Ed where you actually go and experiment with this kind of thing. Do you remember which, was it in this week's chapter?
It was in a tutorial section.
In a tutorial section. So hopefully you'll get a chance to play around with that. Okay, so that's that demo. Now we have 2 more fun demos to go. So in this one, I am going to increase successively larger amounts of memory. How much memory? Every time I am going to increase the amount by 10,000. And let's see this one work. All I'm doing here is allocating those bytes and assigning an integer. Have an array of pointers, and inside that array, I'm storing the different allocations, so a pointer to each of the different allocations. So let's say I've allocated 10 chunks of memory. In my array, I want to store pointers to each of those 10 chunks. And that's what I'm doing here. It was right, I was wrong. There we go. I'll run this once more just to make it appear nice and big. There we go. So we can see that malloc of 10 bytes succeeded. Malloc of 100,000 bytes succeeded. Malloc of 100 million, is that a billion or 100? Let's see, 3 zeros, another 3 zeros. Malloc of 1 billion bytes succeeded. Malloc of, however, that's probably like 100 billion or 10 billion, I can't quite see how many extra zeros there are, succeeded. And then this giant malloc failed, because that was probably more bytes than I had in my computer. Now you'll notice so that initially seems unsurprising, until you actually go and calculate how much memory my computer has, and you might notice that this succeeded even when it was more bytes than this particular computer actually has. And that seems really surprising. How can it allocate more memory than my computer actually has? Does anyone have an idea? Aiden, you have the microphone at the moment, right? Why might my computer permit me to allocate more bytes of RAM than my computer has? Think back to one of our discussions earlier today.
Could it be using the hard drive?
So when we do the allocation, we aren't actually already using that memory. What we've essentially done is the operating system has given us permission to use that memory. And so we're not immediately, our computer doesn't immediately start this thrashing thing where we've run out and nothing more can be allocated. Our computer is a bit cleverer than that, and by computer I mean the operating system. So the operating system can give you permission to use more memory than it actually has available in RAM, or even than, in theory, than it has available in total. And so what's actually happening behind the scenes is it's deciding, okay, is this a memory allocation that in theory I could support? And if it thinks that, then it's going to allow it to succeed, and if not, it will cause it to fail. So this number was so preposterously big that the operating system said, that's totally unreasonable, I can't address that amount of memory, it's got to fail. For a smaller amount of memory, the computer said, well, maybe what will actually happen is that person won't end up using all of that memory right away. They'll just end up using small chunks of it, and all they wanted was permission to use some of those chunks. So it's speculatively saying that, maybe I'll have to use swap, maybe there isn't enough in RAM, but for the time being, this isn't actually a problem. And so that's a really interesting behavior of malloc that one wouldn't necessarily expect to see. And let's open one more program. And this is actually a practical use of using it. And this is where we'll end for today once we've looked at this. Maybe. Okay. So the basic goal of this program is to take a very large input, a very large text, break it up into a sequence of words, and then say which of the words are unique out of the whole set of words in the text. So the word "the" is going to be repeated in a book lots and lots of times, but we want to print a list in which every word is repeated only once. So we have our usual includes. We're going to set a maximum length of a given word so that we can a priori figure out how much memory to allocate for a word. And then we're going to initially just store room for 100 words. We've got a type def, which is just going to be our word t. So this is going to say, for every word, allocate 1,000 letters, plus 1 for null byte. Yeah. And then we have some functions up the top. And this is where things start to get a little complicated because we're now using all of the techniques we've done in the class put together. So current size is going to store the size of the word array that has how many, the maximum number of words that we can fit in our array. So this is like, if our array is of size 100, that's going to be our initial thing. Notice that current size does not refer to how many words are in the array. That refers to the size of the memory that we've allocated at this point. And then we have a char star star. And who remembers what a char star star is? It's dereferencing twice. What else is it? Pointer to a pointer, yeah. It's an array of strings is really the best way of thinking about it, because one char star is a string, so a char star star is an array of char stars, and an array of char stars is really an array of strings. Okay. We're going to keep some variables to keep track of things, so how many distinct words have we found so far? How many total words have we been through? And then what we're going to do, we're going to malloc some space for the words, and how much space do we need? We need space for 100 initial words, and each word is going to be the size of one of these char stars. So this is going to be a single char star pointer. So there we have our malloc. Then we have exit if null, which is just a quick function that's going to check if malloc succeeded. So that hides some of the logic that we already did previously. And this is where our code really gets serious. Yes, Toby? Size of a pointer. Yeah. Yep, because we want to store pointers to all the different words. But yes, good picking up on that. That's exactly what we wanted. So we're going to run this function getWord, and let's leave the details of that for a minute. And every time we get a word, increase the total number of words that we've read by 1. Do a linear search through all of the words that are already in the array. And we're going to use string comparison to see if we find that word in the list. If we don't find the word in the list, then what we're going to do is first thing we're going to do is we're going to check if there's room in the array in the memory that we've allocated for the new word. Because if there's not room for it, then we're going to screw up unless we create room for it. So the first thing to do is to check, have we used up exactly the amount of space that we had available already? So this is the number of distinct words, is the number of words that we've already read in, the number of words that we'd made space for. If that's the case, that means it's full. And if it's full, double the current size and actually allocate the memory for that. And so we're using Realloc here to copy all the words that were previously in that smaller array over and putting it in the bigger one that's twice the size. And then again, just check that that succeeded. Okay, when we get to this point, we know that there's definitely room because we just checked. And if there wasn't enough room, we doubled the amount of space. So if there is space, then what we do is we add to the last position in the array, and the last position in the array is equivalent to the index of the number of distinct words that we've seen so far. So if we've seen one word so far, that word is in position 0, which means num distinct is equal to 1, which means position 1 is free for the next word that comes in. So what we do is we malloc space for the new word, because we've got a new word and we need to actually add memory for that word, not just for the pointer to that word. Because remember, our array that we have, our all words array, contains pointers to those words and does not contain the memory for those words themselves. So if we've got a new word that's just come in, we want to save that word somewhere. And so we're going to create a new memory allocation for actually storing that word and not just storing a pointer to the word. So this function, what this line does is it creates a new allocation for that word and returns the pointer. And where do we store that pointer? We store that pointer in the all words variable. And now we know that we have space for the pointer. That pointer now points to a chunk that's large enough for the new word. Then we copy that new word into the space we've just made for it. And now we can read in another word using our getWord thing into that one word space. So it's a little complicated, so I'd encourage you to, again, go through this one on your own time a little more slowly. What do we do at the end? We go through it, we print it out one by one, each index in all words. And then as we go through it, we free the memory pointed to by that word's pointer. So let's say we're looking at the 5th distinct word. Once we've printed the 5th distinct word, free up the space that the 5th word previously used, and then set that pointer to null. Finally, at the end, remember our big array, our array of pointers, Also, we malloc that, and so we've got to free that too. So there's not just one thing we have to free up. We have to free up each individual word, and we also have to free up the array that contained the pointers for those individual words as well. We set all words to null, just like we do after any free, and then we're done. And how do I have my getWord function? Well, we've already written that earlier in the class. And with that, I've given you back an extra 2 minutes of your lives. I hope you have a great afternoon, and I will see you tomorrow.